So, picking up where we left off on this pipe resonance thing. So this is one, this is another one for the calculator. So what frequency will a 2.5 foot organ pipe produce? Right. Hang on one second. My thing doesn't seem to be happy right now. One moment. There we go. Yeah. So in this case, we're probably talking about a pipe that's closed at one end, open at the other end. We'll make that assumption for purposes of our math. It could be the other way around. There's lots of different kinds of organ pipes. Let's assume closed at one end, open at the other end. So in order to find a frequency, right, we want frequency. What are the two things we need to know? Wavelength and the speed of sound, right? We know the speed of sound. What is the wavelength we're talking about here? Yeah, so we've got to do, wavelength is going to equal 2.5 feet times 4. So what's 4 times 2.5? 10, right? And now, what is 1130 divided by 10? Yeah, so that would be 113 hertz. Yes? Yeah? There you go. We did it. So let's try this one. Okay, same pipe, but you're going to shorten it by 6 inches. So now it's a 6-inch shorter pipe. So what was it before? It was 2.5 feet. So now it's going to be 2-foot pipe. So you're going to be 2 times 4 equals 8 for your wavelength. Now you're going to do 1,130 feet per second divided by 8. Somebody pull that up on their calculator and tell me what you get. 141.25. So here's my deal. It's not right until 3 people get the same answer. So 2 other people do that math, make sure that that's right. This is like medicine. It's like, do you concur, doctor? Do you concur? Do you concur? Got to get at least 3 people to get the same answer, including me. You got that answer? I got that answer. Sam got an answer? Okay, it must be right. If 3 people get the same answer, pretty good chance it's right. All right. Okay, so here's one that might take us a few minutes. What are the 3 fundamental resonant frequencies of a room that is 16 feet by 6 foot by 8 foot? Okay. So let's do this. Let me do this in black. So let's do some sort of a orthographic diagram here of this hypothetical room. Okay, if I draw that, does that make sense? Okay, so this is some sort of a room, right? So what we're saying here is that we've got, it's 16 feet by 6 feet by 8 feet. I'm talking about the distance between walls. So like from this wall to that wall is, we'll say 16 feet. I mean, this is obviously not to scale, but get the idea. And then from the front wall to the back wall would be maybe 6 feet. Okay, and then floor to ceiling would be 8 feet, right? That's what we're talking about here. Does that make sense now? Okay, well, guess what? Every time you've got parallel walls, so like between this side wall and that side wall, that's an enclosed space, right? There will be a resonant frequency for that. Front wall to back wall, that's a different size enclosed space. You'll have a resonant frequency for that. That floor to ceiling, that 8 feet, that's another resonant frequency, okay? So now we just got to do the math. So so if we talk, let's start with the 16-foot one. So we'll call this A, that B, and that C. Okay, so A hertz is going to equal, if I just write this all the way out, it's going to be 1,130 feet per second divided by 16 times 2. Okay. So that would be otherwise known as 32. So 1,130 divided by 32. We get
335.3125.
That's what I got. Did anybody else get that? Yes? Maybe? No? Okay. Okay, so B hertz is going to be 1,130 feet per second divided by 6 times 2. Yeah? So 6 times 2 is otherwise known as 12. And that would be, so that would be 1,130 divided by 12. Whoa, hang on, go back. There we go. Yeah, I got 94.167 is what I got. Hertz. Anybody else get that? Yeah, Nora got that? Okay, Andre got that? Okay, so C hertz is going to equal 1,130 feet per second divided by 8 times 2, otherwise known as 16. And that gives us, I got 70.625. Yes? Yeah? Anybody else? Yes. Okay. There you go. We did it. Okay. All right. So we good with that? We good with that math? That makes sense?
Yes.
All right.
Lovely. We actually get to learn this.
So, so we've learned a few properties of sound waves so far, right? We've learned that they have a speed that is fairly predictable, although a moving target. But you can kind of predict how it's going to move. We know that it has that it follows a predictable pattern in the way that it oscillates, right? That you have this pattern of compressions and refractions in the air, and every time it does a full compression and a full refraction, that's a cycle. And the number of times you do that every second is what's called the frequency, and that tends to correspond to pitch once it enters our ear-brain system. We know that. We also know that given the relationship of that fairly predictable speed of sound and that fairly predictable frequency of oscillation also results in a also predictable distance or length that it travels in order to complete these cycles. We call that the wavelength. So those are the 3 properties of sound that we learned on Monday, right? So there are a few others, though, that we haven't talked about yet. One is called amplitude. We touched a little bit on amplitude on Monday, but we're going to talk quite a bit more about it today. So amplitude is, you know, if you look at the graph, you know, the difference between this top left wave and the top right wave is amplitude. Okay, you see how that compression peak is higher and the refraction peak is lower. So that means that if this is a graph of actual air pressure amplitude, then the air molecules were compressed more in the higher amplitude one, and they were stretched apart more. Okay. What does that mean? Well, it just means that they were compressed more and refracted more. Once that enters your ear-brain system, you tend to interpret that as loudness. Okay? So that higher peak, or that higher amount of compression and that higher amount of refraction sounds louder to you. Okay? Less compression, less refraction is quieter to you. We call this amplitude, the amplitude of the wave, because as you'll see and you'll learn, we don't just deal with sound waves in the air. We also deal with them in electrical form, in various electrical forms on wires and things like that. And those also have an amplitude, even though they work almost completely differently. So amplitude is generally what we would correspond to loudness. Now, there's another property called the phase. Okay? So remember, because of that relationship between the speed of sound and the frequency, how fast it does its cycles, there is a distance involved there. But we also know that distance is time in sound, right? There's a intimately connected relationship between that wavelength and time. If it takes a foot for that frequency to complete a cycle, it also takes about a millisecond for that to happen, okay? And so when we talk about phase, what we're talking about is time. Where in time are we in this compression and refraction pattern? Because yes, when we get to that peak, there is a distance involved there, a physical distance in a sound wave in the air, but there is also a period of time that it took to get to that point, and that is phase. So which phase of the wave are we in? Are we in the compression phase? Are we in the refraction phase? Or are we somewhere in between? Okay? And depending on which phase we are in of that wave, there is a certain amount of time that has transpired. Okay? So when you think about phase, start getting in your head that that is time. Time is phase. There is another property that is different, but usually, often, almost always misunderstood, which is polarity. Okay? And polarity comes into play when we start converting these sound waves into different formats. So we convert them all the time, right? So a microphone is a transducer that converts an air pressure sound wave into an electrical alternating current wave. Okay, a loudspeaker does the opposite. A loudspeaker takes an alternating electrical current signal and converts it back into a sound wave. When you do that, anytime you do that sort of a conversion, you run the risk of having a polarity problem. Because the mechanism that does that conversion interprets that compression of air molecules into something that happens electrically or digitally or whatever, and it converts that refraction into something that happens electrically. So if the compression hits whatever that transducer is, like the microphone, do you want that to represent an upward tick in that voltage wave, or a downward or a negative tick, like a positive tick or a negative tick in that voltage wave, right?
Negative, yeah.
It depends, is the answer, right? It depends. But that is polarity. So
Various equipment will have a different polarity based on the way it is designed.
yeah, absolutely, yeah.
Like when you are designing a microphone, you can choose whether or not you want.
Good equipment will tell you what they decided to do. Good equipment will say, a positive pulse of air pressure will result in a positive voltage amplitude, right? Some don't always do that, right? But you should start looking for that,
So
okay?
do you then account like if you have equipment that is out of mismatch?
Ah, very good question. So in some cases, this might be on purpose, okay? There might be a really good reason why they did that. But most often when you end up with a polarity problem, it's because something went wrong. Okay, like you wired up the connector backwards, or something. That's what happens most often. Is you wired a connector backwards. Okay. Now here's the important thing: we can't hear polarity. Right?
It doesn't change the way that audio is.
No, it doesn't change the way it sounds. Right. Yeah. I mean, it is an actually inverted thing. So, an inverted polarity wave would be like this, right? If I took this one here, this A2, it would be that, right? Send that through a loudspeaker. It's going to sound exactly the same for us. It's just out of polarity. So you can make that mistake a lot and maybe never even notice it. But you do notice it later if you end up in a situation where you've got one copy of this that is in a certain polarity and another copy of this that is in a different polarity, and then they start running into each other, either electrically or in the air. And when that happens, we can hear that, okay? And that becomes a problem, which we'll explain in a moment. The reason I'm saying that this is widely misunderstood is because a lot of people really confuse polarity and phase. Okay, remember, phase is about time. Where are we in time in this process of oscillation? But polarity is just something got backwards. Something's happening backwards. Okay? And there's no time involved in it going backwards. It can go backwards at the same time it could go forwards. Right? There's no time involved there. But notice well, let me see if I can put one in here. So I could have a second wave here that is out of phase, right? So if I start a new one there was a period of time involved there, right? And that would be phase. I am now, if you think about this as a circle, right? You start here, and we could call that 0 degrees. And then we go through a cycle, we end up back at 0, so that's now 360 degrees. Okay? Then, here in the middle would be 180 degrees. This would be 90 degrees. This would be what?
180. Or, I'm sorry,
270 degrees. There we go, making sure you're following along. Okay?
I heard 90.
So here, I would, if I had another copy of this sound that was 180 degrees out of phase, in other words, there was an amount of time that had transpired. It could be a little bit of latency. It could be a lot of things, where I start generating the second wave, and it's 180 degrees out of phase just because of a time offset. Well, for a sine wave, which is just a pure tone like this, that would look and sound pretty much the same as it being out of polarity. Right? You wouldn't really notice the difference, okay? Even though something very different has happened, right? The out of polarity is a wire is backwards. The out of phase thing is something happened in time. But for a pure tone sine wave, they are, that looks like the same thing. However, in real life, we never work with pure tones, ever. Okay? No sound that you have ever heard in your life, except for possibly maybe a feedback frequency. Other than that, you've probably hardly ever heard an actual pure tone. Okay? Everything else you've heard is what we call a complex tone. And what I mean by complex, it has lots of frequencies happening all at the same time. Very few times you've ever heard just one frequency happening. Okay?
David was talking to us about in our audio electronics class about harmonics. Is that what you're referring to?
Yeah.
As a complex.
Yeah. So when you get into complex what sounds like that, phase and polarity have very different results, right? Because that same offset of time results in a different phase for every one of those frequencies. Every one of those frequencies is going to be at a different phase of that wave based on their wavelength, right?
So it's like nearly impossible to fully cancel.
Yeah, you can't, right? So, however, an inversion of polarity of a complex wave, every single frequency is inverted against itself, right? You see the difference? All right. So let me see if I can drive this home a little bit more. The first thing I want to do is it is. The first thing I want to do is hit home this concept of resonance. Okay, so I found a resonant frequency of this room. Okay, 121 hertz. Okay, so that's 121 hertz. I am generating a pure tone. I'm not sure that you maybe are not entirely hearing a pure tone because there might be some distortion and things going on and things, but this is close to a pure tone. So what I want you to do is, I have found a frequency that resonates. Let me explain to you how I found that. So I can sweep the frequency here. So as I sweep it, I'm listening for one that gets suddenly louder. Okay, so this is like not anything, but whoa, right there, it got louder, didn't it? Okay, why? Because the room started resonating. Okay, so that 121 hertz fits in this room really well, and so it starts throwing a party against itself and gets louder. The amplitude goes up. Okay, so what I want you, it's basically stuck inside this room. So I want you to get up out of your chair and walk the room, and what you'll find is there are places where it's really loud, and there are other places where it almost completely goes away. Okay. So I want you all to find a spot where it gets significantly quieter.
Right here.
Okay? But a different spot. Everybody find a different spot. Not everybody stand at the same spot.
Now, I get that it's resonating all inside the room, but does the speaker placement and point have anything to do with it?
It shouldn't. Okay. Okay, good. So we're finding some spots. Now, what is the wavelength of 121 hertz? Can someone sort of earball that for me? Okay. So it's around 10 feet, right? How far apart are you all standing? Look how far apart these two are. Look how far apart those two are. 10 feet, 10 feet, 10 feet, 10 feet, 10 feet. Magic. Right? Okay. Okay, so that's resonance, right? So we resonate the room, and we can kind of make it, it's called a standing wave. We can get that frequency to kind of get stuck inside the room, and you have these places where it's really loud and places where it's really quiet, because it's not really being allowed to propagate very efficiently. Oh, it's a fun trick, right? Cool party trick. Okay. So now let's take a look at what this phase and polarity thing's all about. So here I've created a 400 hertz wave, and I'm going to create another 400 hertz sine wave. Okay, so what you notice is these are currently in phase with each other, perfectly in phase. So if I start with the first one, you can see that this is the resulting wave over on the right. And now I turn it back on, and what happens? The amplitude went up. Why? Yeah, they're summing together, right? This energy is summing together, and it's perfectly in sync, and so those two compressions are working together to get a higher compression, right? So that's the first thing that happens. Now, watch what happens as I start messing with the phase of the second one. So I'm just going to offset the phase of this second one a little bit and look at that combined waveform. See how it's getting quieter and quieter? So, see if I can slow down the scope a little bit. Okay, so look, I'm almost completely inverted here. Not quite. Okay, you see how it's still a little off, which is why it's not perfectly canceled out, but I just wanted you to see that that's what's actually happening. So let me see if I can get it perfectly. If I go a full 180 degrees, it's basically completely canceled out. I did that with time, right? So I am just adjusting the phase or time of that second wave, and it cancels it out. Okay? Now I'll take it back to in phase. Now watch what happens if I just invert the polarity. Right? I get the same result, right? Now that's for a sine wave. Let's go to something a bit more complicated. Okay? Okay, so this is just one track all by itself, right? And I'm going to add a copy of it in phase. Ready? Okay, it gets louder, right? These are perfectly in phase, and so it's getting louder. Watch what happens, though, when I start messing with time. Anybody hearing anything yet? Not much, right? I'm not even sure the phase can really manipulate that wave because it's just too complicated, right? What am I actually manipulating? But if I do a polarity inversion, I get it, right? Okay, so phase and polarity are not the same thing. Okay? So with a complex wave, that interaction is much trickier. Let me show you actually, let's go back to this thing for a second. Any questions about any of that? Phase, polarity, amplitude? Is that kind of making sense right now? Okay. So these are the kinds of things that happen when two sounds combine with each other out of phase. Okay? So if there is a 180-degree difference in phase, you get a cancellation. Okay? If there is a 0-degree relative phase, or so 0, 360, some sort of thing like that, you'll get a reinforcement. It's called a reinforcement, so it helps each other. It gets louder. Amplitude goes up. Okay? And then there's some things that can happen in between. For example, a 90-degree relative phase, the amplitude will go up slightly, but the phase of the combined wave gets offset a little bit. You see that? See how the combined wave has a different phase of the two source ones? Here's an interesting one. 120 degrees combines to have no change in amplitude. Like they're off just enough that they don't change the amplitude, but the phase of the resultant wave is offset by 60 degrees. Okay, but there's no actual change in amplitude. So this is for sine waves. If you have a complex tone, which a complex tone has harmonics and all these different frequencies all happening at the same time, guess what? All of these things are happening at the same time for various frequencies. Okay, so some frequencies are getting canceled out, some are getting reinforced and louder, some are barely getting louder, but the phase is getting shifted a little bit. Some are not getting louder at all, but the phase is being shifted. So it's like the whole thing just gets really messed up when you start combining two complex sounds slightly out of time. Okay? Here's what that looks like. So I've got two simple examples here where I've got an offset of time of a sound, of a complex sound. Now there is some frequency where that offset of time is going to result in some multiple of 360 degrees offset. That is going to get louder, right, when it goes together. But that same period of time for a lower frequency is going to be a 180-degree phase shift. And that frequency will get a lot quieter, almost completely gone. Okay? And all those things in between. If you were to graph that, this is what the frequency response would look like. So on the horizontal axis is frequency. The vertical axis is amplitude. Okay? This is the graph of the amplitude of all the various frequencies when you combine two of them slightly out of time. You've got all these ones where you get this big dip, those are ones that were some sort of 180-degree phase shift. These ones that got a little louder, so the starting sound was probably 100 at 100. You see how there's some frequencies that get louder than that? That's because they were combined at some multiple of 360 degrees, right? And then there's all these things in between. This is called comb filtering. And we call it comb filtering because when you do the graph, it looks like a hair comb. Okay? You know, like combing the desert. Remember that from Spaceballs? You've seen Spaceballs?
Yeah. Whoa.
We're combing the desert, and they had a big comb that they were. Right. Yes.
Spaceballs class?
That would be white
I vote magic school
when
master.
generating this. That would have been
This actually was generated using a swept sine wave. So I created this in fuzz measure, which we used in intensive arts. So what I did is I put a swept sine wave out of two different loudspeakers, and one of them had a 1 millisecond delay on it. And I put a measurement mic in and measured, what happened at the microphone when those two sounds hit each other in the air. And this was the result. Okay.
So the graphs on the side, what are the numbers T1 and T2, those variables?
Difference of time.
Okay, so time of one signal to time of the other.
Yeah. So that same, what I'm saying is that same amount of time. It's the same amount of time in both cases. It's just the result is different depending on which frequency you're talking about. Okay?
So in this case, it would have just been that 1 millisecond.
Yeah.
Difference.
Yeah.
As long as the mic was right in the center.
Yeah. Yep, a millisecond of difference. So in this case, a millisecond for this frequency would be a reinforcement, or multiple. There's lots of frequencies that would happen to, or that same millisecond for some frequencies would result in a cancellation. Okay. So you want to hear what that sounds like? Yeah. Okay. So, nope, this one. Let's hear what that sounds like. We're going to do it with pink noise first. Okay, so here it is. I'm creating two copies of the pink noise. So double pink noise signals, but they're combining at the same time. Okay? I'm going to start delaying one of them a little bit. Okay? Okay, so you see how we're up here is these two things are frequency response. Just this one's logarithmic, this one's linear. We'll talk about that later. But so look at the logarithmic one. You can see we've got some frequencies are getting canceled out, some are reinforcing. Okay, you can hear that. But what you can also hear is as I change the delay, the frequencies that are affected also change.
So then, in the example that you gave us with the 1 millisecond delay,
Yeah.
the period of that you were generating was 2 milliseconds? Or some multiple of?
No, it was a 1 millisecond difference between the two sounds.
Okay.
I'll do that. I'll do that exact thing right now.
Okay.
So I'll switch to milliseconds, and we'll go to 1. There it is. 1 millisecond difference between the two sounds. Okay? As compared to 0 milliseconds. That's what pink noise sounds like. Okay? And then I go to 1 millisecond of delay, and this happens. Okay? That doesn't sound super awesome. Now, here's the other thing to keep in mind. I'm sorry, I was on white noise, not pink noise. Let me do pink noise.
How dare you?
Ah, much better. Okay. So, 'cause here's the thing that happens is, usually when you have an offset of time, it's not consistent. So imagine, well, it's not consistent for a lot of reasons. We'll start there. Most things that are going to cause an offset of time between one signal and another is not going to be a consistent thing. And so it's not just that your sound's getting obliterated, it's getting obliterated inconsistently. So as I wiggle the time a little bit, You hear what's happening? Anybody ever used a flange effect?
Yeah.
Okay,
Flanging is doing
that's what it is. It's creating a comb filter that moves, right? Here, I'll make it. Here's your flange. Right? There you go. So, what you're hearing right now is what I call comb filtering on the wire. Okay, and comb filtering on the wire is when the two sounds run into each other electrically, like inside of an electrical circuit or a digital circuit somewhere. Okay, so they get delayed somewhere inside of your sound system before it comes back out of the loudspeaker. And in there, it gets mixed together. So somehow one of the two signals gets delayed a little bit, and then they get mixed together. How would they possibly ever get mixed together? In your mixer, right? That's like that's what it does, is it mixes sounds together. So if you mix these two sounds together and those two sounds are the same, right? This only happens if it's the same sound, right? Same in every way. So, or really, really close to the same. Same in content, same in amplitude, same in everything, right? But the only thing that changes is time. So then you mix it together, and then this happens on the wire. Now, comb filtering that happens on the wire is comb filtering that everybody hears no matter where they sit in the room. Okay, it comes out of the loudspeaker already messed up. Okay, that really, really stinks when that happens because everyone hears it. Doesn't matter where they sit or how much they paid for their ticket or whatever. Everyone hears that garbage. Okay, but you can also comb filter the air. You want to hear what that sounds like? You want to hear what it sounds like when you comb filter air?
I have a question about the
Yes.
on the wire. So that's delay that you can apply, obviously through processing, but also latency. So if you run into
Sure.
that, would you be able to fix it by popping a multiple of?
Yeah, sure. So like if you can figure out what that delay was, where that happened, then and if it was consistent,
Yeah.
then yeah, you could offset it, by basically delay the other one by the same amount, and then you get it to line up.
Does it have to be by the same amount, or could it be a multiple? Like if it, because from, my base understanding of this, it's that multiples of that period cause the comb filtering. So if it's 20 milliseconds of latency and that's causing a big problem, could you do a 10 millisecond delay? And
It would fix some of it,
but not all.
but not all of it, right? Because it would have to be exactly the same delay for all the frequencies to line back up,
Okay.
right?
That would, gotcha. Yeah. Okay.
So, yeah, that is possible, like to fix it that way. Sure. Let's hear what that sounds like with music, actually, before I do it in the air. Okay. So here's your comb filtering on a wire. This is what happens with actual music. So there's your flange effect, right? Well, lo-fi means basically it's comb filtered like crazy.
And then they asked for him to be set.
Right? That term flange actually comes from the days of tape. So there's actually a component of a reel-to-reel tape deck that is called the flange. Okay, and it controls the tension of, among other things, of the tape. And what they found is, and I believe it was George Martin that figured this out, that if you wiggle that a little bit, it actually torques the tape a little bit across. It goes across the record and play head, so it's hitting it diagonally, which means one channel of the tape is going across the head at a slightly different time as the other channel. And then you mix that together, and it has the comb filter, right? And so if you actually go and wiggle that a little bit, it's doing this to the tape as it goes across, and it sweeps that comb filter back and forth. Okay.
Jason, quick question for you for comb filtering. What correlation does the amount of time have on the cancellations? I know that you probably already answered this question.
We're gonna get to that mathematically, but yeah, it changes. So basically, it's about which is that first frequency to cancel out, and the longer the time, the lower that first cancellation is.
Does more time necessarily equal more comb filtering?
Yes. So the more delay or more offset of time, the more cancellations or reinforcements you get. Okay, but it also starts at a lower frequency.
So you can't. Oh, yeah. So the more time you have, the lower you're starting at. So you have all
Yeah.
this headroom to
Yes, exactly. Exactly. All right. So, all right, let's do it in the air. Are you ready? We're going to comb filter the air. So here's what you're going to want to do. You're going to want to get up out of your chair, and you're going to want to try to stand right in the middle here of the two speakers. So find the spot where it sounds like the comb filtering is coming from the sub, basically. You can line up, behind each other or whatever. Okay. You ready? So I'm going to comb filter the air. You hear that? So here's I'm going to do the 1 millisecond. Actually, I'll do it like 7. Okay. So no, I'll do 2. So move your head around a little bit. Like go a little bit to the left, a little bit to the right. Okay, just maybe even walk a little bit like this. And listen to what happens. Listen carefully. You hear that? So now you're the flange. Right? So here's the problem with comb filtering in the air. Everyone hears something a little bit different, depending on where they stand or sit, right? That's a different kind of problem. Okay? So either way, it's a problem, but it's a different problem. If you let it comb filter on the wire, everybody hears the same problem, and it's bad, equally bad for everybody. If you let it comb filter in the air, everyone hears a slightly different problem. Neither of those scenarios are really super awesome, but here's the good news. You have never in your life heard a completely uncomb filtered sound.
What about from a single speaker?
Nope. You have never in your life heard a completely uncomb filtered sound. Why? Because what happens to that loudspeaker when it makes sound? Where does that sound go? It goes everywhere, actually. I mean, we like to pretend that loudspeakers are more directional than they actually are. But even really directional loudspeakers still send the sound everywhere. It's just some of them send it less everywhere than others. But it goes everywhere. So some of it goes directly to your ears, but the rest of it goes everywhere else. And when it goes everywhere else, it bounces off of things, right? So you hear that sound many, many times. You hear it, yes, directly from the loudspeaker to your ears, but you also hear it bouncing off the floor and then to your ears, and bouncing off the wall and then to your ears, and bouncing off the table. You're hearing my voice right now, and it's comb filtering in your ears, okay? Because my voice is bouncing all around this room.
What about something enclosed, like a closed back set of headphones? Because at that point, all the reflections you have are within the ear.
Well, so it sort of kind of depends on how swanky your headphones are. Because there could be some weird reflections and comb filtering going on inside of that whole, well, no, like inside of your ear system, like as it resonates and bounces around. Or there could be some distortion of time in the way the driver reproduces the sound to begin with.
I'm just thinking the reflections in such a small space as your ear canal.
Yeah, but even think about the recording, right? The recording has comb filtering in it, right? So it's like you really probably have never heard a completely uncomb filter sound in your life. Right. Okay. And so the good news here is that we as human beings have, basically never heard any sound where this isn't happening, and therefore we've developed and evolved some blind spots to it. Okay, because if we had to go through our entire life, hearing garbage, it would be really difficult for us to communicate with each other, right? If my voice really sounded like that pink noise sounded when I comb filtered it on the wire, yeah, like we could not talk to each other. We couldn't get a whole lot done, just generally living on this planet. And so we have developed some blind spots for dealing with this. We're actually pretty bad at hearing comb filtering in the air. Okay? We're pretty bad at hearing that. because we have had to get bad at hearing it. Because if we were really good at hearing co-filtering in the air, we would go insane, okay? And so our ear-brain system has evolved some blind spots to that. I have to create a very controlled situation in order to let you actually hear comb filtering on the wire, or comb filtering in the air like that. I had to create pink noise, which is a very consistent signal, equal energy per octave, and I have to get you to stand in just the right place, and I have to get the loudspeakers tuned just the right way, and in order for you to really hear that, okay? The same experiment would not work the same way on a piece of music. You want me to prove that? Here we go. So get back out of your seats. I'm going to do the same thing again, same 2 millisecond delay, this time with the music loop. Okay, so find that same spot you're standing in. It's doing the exact same comb filter it was doing with the pink noise. So I'll take it back to the 0. I'll toggle it, okay? So no comb filtering. Okay. Okay. If you pay attention, you can hear a slight change, right? But it's not very dramatic, right? And if you move your head now,
I can only do it at like the low frequencies. The high frequencies sound the exact same.
Can you do it? Can you make it do the confounding on the wire so we can hear that?
yeah.
It's just too weird. They're particular.
No, but it's not affecting the low frequencies.
So here's the wire.
Oh wow.
0, 2.
But that's the exact same interference.
Yes.
Wow.
But because it's happening in the air, you don't notice it as much, right? And there's some reasons why. It's because it's actually hitting each of your ears at a slightly different time, and that's something in your brain in a slightly different way. But also just your brain has gotten really good at realizing that that's a problem that it wants to ignore. Okay? It's not that it's not happening. It's just that your ear-brain system is deciding that
It doesn't matter.
it doesn't care, right? And it's just going to like pretend that that isn't happening. Okay? Yeah, I mean, I think Andre made a good point of you notice it more at the low frequencies than you do the high frequencies. So, and there's a reason for that that I'm going to show you in just a second here. But basically, so there is this concept called, depending on who you talk to and which book you read, it'll be called critical bandwidth or equivalent rectangular bandwidth or something like that. And what that means is there is a range, a frequency range, and that's a bit of a moving target depending on where you are on the audible spectrum, where dramatic changes of amplitude within that range are like outside of your ear-brain resolution to hear, right? So you can manipulate amplitude within a certain range of frequencies, and you don't register it, okay? That averages out to be about 1/3 of an octave. I mean, it's a little bit wider at the low frequencies and a little bit narrower at the higher frequencies, but generally it averages out to be about 1/3 of an octave. So any messing around of amplitude within 1/3 of an octave range, you're not super good at hearing that, okay? Which is, so if we go back to the graph, notice how as you go up in the spectrum, those peaks and cancellations get closer together. And eventually you get to that range where that's happening within that critical bandwidth, and you start ignoring it, okay? It's harder to ignore it when it's happening on the wire, but when it's happening in the air, you're really good at ignoring that. You've had to, right? You've had to get good at ignoring that, okay? I don't know. Yeah, I don't know. But so one of the reasons that, well, so given that we know this, given that we know that we're not super good at hearing comb filtering in the air, we can use that to our advantage because we can't ever have no comb filtering. Like, just welcome to the rest of your life. The rest of your life is going to be dealing with comb filtering because it's always there, and you're just trying to make it, not. You're trying to make it not as noticeable as possible, right? So you can't make it completely go away, but you can get it to where it's not hurting you as bad as you thought, okay? And one way of doing that is to basically make it so bad that you put the entire frequency audible spectrum into critical bandwidth. So as you increase delay, this whole graph shifts down. Okay, so if you can increase the delay such that this first cancellation is way down here at like 50 hertz, then all these cancellations and reinforcements get so close together across the audible spectrum that you ignore all of it. It's a similar concept to like when you're watching a film and you're really seeing like 24 still pictures every second, and your iBrain system, you know, stitches that together into one continuous thing, even though you actually just saw 24 still frames. Okay, similar kind of idea. In this case, you know, the comb filtering gets so bad that your brain system says that can't possibly be right. That can't possibly be how this is meant to sound. And it just sort of smooths it out and fixes it.
Sweep it up and it just gets terrible, 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 and then starts to get, like, we hear it as getting better.
Yeah. Yeah, so I can do that too if you want. So let's see here.
I know this is probably going to be, it depends, but what's easier, creating less comb filtering or creating more comb filtering?
It's way easier to make more than less, generally. But okay, so here we go. So I'm going from 0 to 1. You can probably all hear that. 2. So tell me at what point you stop hearing it change. Let me go back down to 8. Yeah, somewhere around 12, 13. It's like I'm not really making a difference anymore. Why? Because it's getting so bad your brain's like, okay, that can't possibly be right. I'm just going to ignore that. Eventually, you'll start hearing double. I would expect to hear double by now. Maybe there's a range of how I can do this. I'm out of range. Okay, so, right? Eventually it got to where I was changing it by a millisecond and it wasn't sounding any different, right? That's because we got to that critical band point in your ear. And everyone's going to be a little bit different, right? Everyone's critical band is slightly different. But generally speaking, once we got around past 10 or so, everyone was like, okay, yeah, it's not really changing. It was still comb filtering. In fact, every millisecond I added, it got worse. The comb filtering got worse and worse and worse. It just eventually gets bad enough that you reject it as an error. You're like, I'm not about that. I'm not gonna sit here all day and listen to that. Okay. So that is one way of dealing with it. Another way of dealing with it is like never letting two sounds that are the same combine out of time. That would be super awesome if you could pull that off. And sometimes we try to do that. But that's not always possible. It's actually never completely possible. But there are a few things you can do. For example, well, let's think about some scenarios. Like, what are some scenarios where you could create a situation where two sounds combine slightly out of time?
When you're sitting with a front fill and a main.
Yeah. So maybe you've got two loudspeakers pointed at a listener, and they are a different distance away from that person, right? And they're producing the same sound. Yeah, those two things are going to hit that listener at different times, and it's the same sound. It'll comb filter. Okay. So yeah, your options are you delay the one that's closest so that it arrives at the exact same time as the other one, and then it won't comb filter. But that only works for that specific person. The person in the seat next to them, it's not going to work for them because now that time relationship is slightly different and it won't be perfect, right? But sure, like if you only have one listener, yeah, you could do that. Any other scenarios where we could create the experience of hearing two sounds combine slightly out of time?
When you have
Yeah, so maybe like their sound goes into their mic, then comes out of a speaker, and that speaker gets back into the mic, and you can and you don't get to the point of feedback, then yeah, there'd be a little bit of comb filtering happening there. That's one of the reasons why we really don't like to put vocals in monitors for musicals. Yes, it's about feedback, but it's also about that comb filtering. Like it would sound really bad when that sound comes back up into the mic. Yeah, any other scenarios?
Anytime you have two people who are both mic'd,
Yeah.
they're close enough that the other person's mic picks up what they're saying.
Yeah.
So like if I was standing next to you,
Yeah.
and I had a microphone on,
Yeah.
what I was saying was being picked up by your mic, and what you were saying was being picked up by mine.
Yeah. So if we're standing a foot apart from each other and we're both wearing an omnidirectional mic on our forehead, our voices would be picked up off each other's mics, and that a foot is a millisecond. So there's a millisecond of difference between those two mics, and you mix them together, and that's going to comb filter on the wire, guaranteed. Okay? There's another scenario where you could have two microphones pointed at the same thing at a different distance, right? Anything, right?
But I mean, sometimes you kind of want that in a kit. You want that variety.
Yeah, but what I'm saying is, like, if you've got two microphones picking up the same sound at a different time, it will comb filter,
Yeah.
right? So, this is where I really discourage you guys to read books or watch YouTube videos about microphone placement, because most of the things that you'll read about that are all about recording studios, where they have a very controlled environment, and they're looking for like the best place to put the mic to get the best sound out of that thing. And in live sound, where we don't get to spend a month mixing this and tweaking it and getting all the problems out of it, we get one shot and it's right this second. Okay, our strategy for mic placement is about isolation. We want to figure out how to mic that thing so we're picking only that up and nothing else. And none of the other mics are picking that thing up either, right? Significantly anyway. That's our strategy, because if we do what the books say and put every mic on a 10-foot boom up over the head, it's going to pick everything up on every mic at a different time, and it's going to comb filter like crazy. And we don't have the luxury of being able to fix that, because you can't fix that in real time. Okay, so we tend to try to stick tight. So these are some examples of like how you can avoid it, because the comb filtering happens when the two sounds are identical in every way except for time. So if you can get your mic placement such that this other mic that's next to it is pointed away from it, therefore it might be picking it up, but it's picking it up significantly quieter, then you're changing the amplitude of the two sounds. Right? One is a really high amplitude and one is the really low amplitude. And yes, they're out of time, and yes, you sum them together, but the amplitude is different enough that you don't get a perfect cancellation or perfect reinforcement. It doesn't comb filter as much. Okay? So there are ways of mitigating it. In the case of like the two people wearing omnidirectional mics and they're picking up with each other, see if you can get them to stand a little further apart. Right? Because if you get them further apart, two things happen. Time gets longer, and longer time means more dense comb filtering. It's easier for us to reject it. But the other thing that happens is the pickup between the two mics gets quieter in amplitude. The difference in amplitude is more dramatic, and therefore you won't get perfect reinforcements and cancellations.
Can
So,
a change at either 1 and 2 feet, or even
Yeah.
less than that, really change the amplitude enough to help?
absolutely. If you can double their distance away, if they are 1 foot away and you can go to 2 feet, guess what? 6 dB difference now between those two things. That's enough to have it not comb filter. So when I get in those situations, I will always go to the choreographer and the director and sort of say, is there any way we could get them to stand farther apart in this moment? Like I was doing, Best Christmas Pageant Ever, and I had these two girls that were standing on these platforms. They were angels, and they, just for reasons of mixing and complexity, they have this dialogue, and I had to have both their mics hot at the same time. And the one kept leaning over like this. She kept doing this to talk to her friend, right? And I get it, like they're whispering to each other. But every time they do that, she'd get close enough and start comb filtering the mics. And I had to go to the director and I was like, can you get them to stop doing that? Get them to stand like this and just like talk out, and it's like, because it's killing me when they do this, right? And so we gave them the note and they stopped doing it, right? But the other strategy would be to never have both their mics on at the same time, right? If you got somebody standing this close to you, if you can keep it so that you never have both mics on at the same time, then both mics are not picking up the same sound and then comb filtering, right? So this is why the biggest reason why we mix musicals line by line, is so that we avoid as much as possible the scenario where there's more than one mic picking up the same sound. No, it's all about comb filtering. Like, we're trying to avoid that comb filtering. That's the whole reason we do it. There's a lot of people that don't realize that that's the reason we do it. They're just thinking that's how you do it. But it's like, no, we're trying to stop comb filtering. That's why. It's not yet. It's also about gain before feedback, but it's mostly about comb filtering. Okay. All right. So let's see if we can. It turns out you can predict comb filtering. Maybe you've realized this by now. You can predict it. Oops, my remote is not working. All right, we'll go back in. So let's just see if we can drive home some of these concepts. So here's a question that you can kind of like rack your brain about a little bit. So how much delay would I have to apply to one of two 250 hertz sine waves that would make it 90 degrees out of phase with the other one? Can you think about that for a second? Well, I think in order to sort this out, we would first need to know the wavelength of 250 hertz. So just doing this in our head, what's the wavelength of 250 hertz? Be 1,000 divided by 250, 4 feet, right? So 4-foot wavelength. All right. So we're talking about a wave where here's your cycle, and this is 4 feet total, right? Which means this is 0 feet. This is 4 feet. This is 2 feet. This is 1 foot. This is 3 feet, right? You see what I'm talking? See what I'm getting at here? Okay. Well, we know that sound travels 1 foot per millisecond. So what amount of delay would get me to 90 degrees? Well, we know that this is 0 degrees, and we know that this is 360 degrees. We know that this is 180 degrees. This is 270 degrees. And this is 90 degrees. So 90 degrees is otherwise known as 1 foot, which is otherwise known as 1 millisecond. So for 250 hertz, if I delayed a copy of that by 1 millisecond, it would now be 90 degrees out of phase with its twin. Okay, does that make sense? All right. Same scenario, how much delay would I have to do to make it 270 degrees out of phase? 3 milliseconds. Okay, you get that? So, all right. Now, how do you actually calculate the comb filtering? So hopefully now you understand that relationship between time and phase now. Well, it's a little dicey, but this is basically the algorithm. So we're going to define some variables here. One variable is going to be t, and that is going to be time in seconds. We have to do this in seconds for reasons that will become apparent. And we're going to define a variable I, and I is going to be, represent one of however many frequencies that we're going to figure out here. Okay. So and then f is frequency. So this is for if we want to find out which frequencies will be canceled out. We could plug in any number for I, starting with 0. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And for every one of those, we could put that in with our value of time, and we would get a frequency that would cancel out. Okay? To find frequencies that would be reinforced, do the same thing. Same process, we just remove the 2's out of that. And we'll get frequencies that get reinforced. So this is basically for all integers that are greater than or equal to 0. And we could go on forever. Comb filtering actually goes on forever. Okay, all the way up into frequencies we can't hear. Okay? So write that down, and then we're going to do some of it. and I will demonstrate.
Jason, do you think it's possible that you could create a canvas page and put these on the canvas page?
Or just send us.
Or just send them to us?
I don't know, maybe.
Okay.
Or like on the server.
I'll see.
Or like anywhere.
It would just be nice to have external services.
You could also take notes.
I am.
Trouble is, if we take notes and we have like one thing wrong and then all about calculations.
Yeah, so make sure you get it right.
Well, it's more like
This formula is in my book, by the way, just for fun. All right, so
On your website, we just have to find the right page.
of course. All right, so let's try this out. So here's a scenario. You got two audio signals that are equal in every way, except for the fact that they are 1 millisecond apart in time. What are the first three cancellations and reinforcements? So when I say that, I mean the first three frequencies that will cancel out and the first three frequencies that will reinforce. Okay, so I'm going to use C for cancellations and R for reinforcements. So 0 cancellation, that means I'm going to put 0 in for I, right? And time is 1.5 milliseconds. What's that in seconds? 0.0015. Okay, so that's our time. T equals 0.00 because it's 1,000 milliseconds a second. So you move the decimal place back 3 places. Okay. So for our first cancellation, which would be cancellation 0, would be 2 times 0 plus 1 divided by 2 times 0.0015. Yeah? Somebody want to try to do that on their calculator and tell me what number they get? So we know that 2 times 0 is 0, right? So you're really talking about 1 divided by 2 times 0.0015. So it would really be 1 divided by 0.003, right? What do you get? Yeah, that's what I got, 333.33 hertz. That is the first frequency that will cancel out for a 1.5 millisecond delay. Okay? So let's take a look at the next frequency with cancel out. That would be 1 for I. So this would be 2 times 1 plus 1 divided by 2 times 0.0015. Yeah, so that would be 666.67 hertz. Yeah? Anybody else get that? I got that. Nora got that. Anybody else get that? Yes? Yeah. Okay. All right. Second cancellation, or third cancellation would be 2 for C. So this would be 2 times 2 plus 1 divided by 2 times 0.0015. I got 1,666.67 hertz. You could also call that 1.67 kilohertz. Anybody else get that? Nora got that? Anybody else? Good. Okay, so there's our first three cancellations. Okay, let's do our reinforcements. So 0 for reinforcement would be, that would be 0 plus 1 divided by 0.0015.
I have a question.
Yes?
Sorry, for cancellation 1, you're going 2 times 1 is 2 plus 1 is 3.
Yeah.
3 divided by 0.003.
Yes.
Right, okay.
Yes. Okay, so
That's 666.67.
yes, you're right. This was actually, yeah, this was 1,000. You lied to me when you guys said you got the same answer that I did.
Oh, well, it's because I messed it up then.
I was reading my notes wrong. So yeah, this is 1,000. this is 666.67 hertz. Sorry, I read my notes wrong. There you go. That make sense? So now 1R is going to be 1 plus 1 divided by 0.0015. And yeah, I got 1333.34 hertz. And then 2 for R gives me 2 plus 1 divided by 0.0015. And I got 2,000 hertz. Yeah? We did it. You can predict it. That's what will happen. Of course, there will be all kinds of other things that happen in between those cancellations and reinforcements. But that is the gist of it. Okay? We've got time. We can do one more of these. You should now be able to do all of the questions in the handout, or the homework. Okay? All of those that didn't make sense to you during the week should now make sense to you. Okay? So let's try this one. You got two loudspeakers. One is 3 feet upstage of the other. And then you measure it at some point downstage. I want to know the first 4 cancellations. Okay, well, the first thing we need to do is figure out T for 3 feet. You remember how we convert feet into milliseconds?
Are we doing with calculator?
Yes.
So then that'll be 1.
We divide by what? 1.13. So 3 divided by 1.13. Because it's 1.13 feet per millisecond. I got 2.65 milliseconds. Okay? Anybody else get 2.65? That's what I got. Andre got 2.65? Yeah, I got 2. Anyways? Okay, good. Must be right. How much is that in seconds? Right. Seconds. We need it in seconds to do this math. By the way, if we had to try to do it in milliseconds, we'd have to add zeros to all these numbers in this equation, which would be really annoying. So it's easier to just do that once and then run the math rather than do it 5 times on every other number. Okay, so I want to know the first 4 cancellations. It's usually the cancellations we're worried about the most because we notice those the most. So 0C is going to be 2 times 0 plus 1 divided by 2 times 0.00265. So 2 times 0 is 0, so you're really talking about 1 divided by 0.00265. I got 188.68 hertz. I need 2 more people to get that before I will accept it as correct. Because I could be wrong. I am wrong often. Yeah? Hey, all right. All right, let's find the next cancellation. That would be 1 for C. So that is going to be 2 times 1 plus 1 divided by 2 times 0.00265. I got 566.04 hertz. Anybody else get that?
Yes, 566.
Okay, I need one more person. Yeah? Andre got it? Okay, good. All right, let's try our next one. That would be 2 times 2 plus 1 divided by 2 times 0.00265. And I got 943.4 hertz. Yes? Anybody else? Yes. Excellent. All right, we got one more to do. 3 is going to be 2 times 3 plus 1 divided by 2 times 0.00265. When I did that, I got 1,132.08 hertz. Huzzah. Anybody else? I got 1132.08 going once and twice. I need a third time. One more time. Yes. Okay, it must be right. Okay. So here's, we don't have time to do these, but I just want to show you how you can invert this. So you could have a question where I could say, hey, here's the first reinforcement. Now tell me what the first cancellation would be. In order to do that, you'd have to find t. You'd have to solve for t and then go backwards. So if it's a reinforcement, if you took this equation for reinforcement and converted it for t, if you know how to do that algebra, I looked up how to do that algebra, and this is what I came up with. T equals I plus 1 divided by the frequency. Okay? And that frequency would be in hertz, so you'd have to take that 1.5 kilohertz and convert it to hertz, so it would be 1,500 hertz. And you would get, you know, a t value that would be the seconds, the delay in seconds. You could then use that to get the rest of it. Okay? So you may want to write down that little conversion to solve for t if you know the reinforcement. T equals I plus 1 divided by the frequency. If you know the cancellation, so here's one that says first cancellation, 640 hertz, and you want to know, in this case, I'm just saying what is the distance involved. You'd first have to solve for t using cancellation. That would be t equals 2 times I plus 1 divided by 2 times the frequency. And you would get the time for that cancellation. And then you just convert that time into distance by multiplying it by 1.13, and you would get an actual distance in feet. Okay? So we don't have time to actually solve that, but that's the order of operations. So write that down, because you might need that little.
I use the cancellation number that we're on. So
Yeah, cancellation. It's the frequency, right? Yeah. Yeah. So you know what the frequency is. So. But yeah, so for I, you would put in 0, right? Right. Okay. So jot that down. That'll come in handy. We don't have time to do that. Don't have time to do that. Okay, I want to just in the last couple of minutes talk about a couple simple concepts. One is diffraction. What's going on here is what happens to a sound wave when you try to put something in its path. Okay? A lot of people think it's no problem at all to stop sound from propagating somewhere, and it's actually really hard to do that. If you want to have any effect on that wave at all, you have to put an object in front of it that is significantly larger than the wavelength of the sound you're trying to impede. Okay? If the object you're putting in its way is smaller than the wavelength, that frequency is going to go around that thing like it's invisible. Okay? It's called acoustically transparent. This is why you can put like grills in front of loudspeakers and it doesn't change the sound.
Is it significantly smaller or just smaller?
Significantly smaller. If it's the same, it will start to have an effect, but not a huge effect. The point here, then the take-home message of this concept is that sound, when we look at, when you would look at like a speaker grill, you would see a bunch of holes. right? But sound sees a bunch of little obstructions. So from the sound wave's point of view, it's all about how big is the thing I'm trying to get around, not how big the hole is I have to go through, okay? So if you're trying to let sound through, you got to pay attention to the space between the holes, right? The size of the holes themselves is not super important. What is important is the space between those holes. And the space between those holes has to be smaller than the highest frequency you want to let through without affecting it, okay? There's another concept called a temperature gradient, where you could have a situation where, and this happens a lot, where the air is a different temperature depending on where you stand in the room. For example, at nighttime, if you're ever doing a show outside, sun's beating down on the ground all day, then the sun goes down. What happens? The air cools off, the ground stays warm for a while. And what happens there is sound travels faster in warm air than cold air, so you've got your sound system shooting down, and what's happening is down where the audience is, it's moving faster than it is up in the air where it's colder, and that has the effect of the whole wave kind of curving upwards, okay? And it gets quieter. It sounds quieter. That can happen indoors too when you got air conditioning up in the ceiling and hot people down at the bottom. If it's a big enough room, the first little part of the show, the first time you fill that theater with people, everything sounds a lot quieter, and you're like, oh, the people are sucking up the sound. It's like, well, kinda, but it's also doing this, right? They're also creating a temperature gradient, and all my sound is drifting up towards the ceiling, and eventually that will settle down, right? That air conditioning will start cooling down those people, and that temperature gradient will be less dramatic. Same thing happens with air. If you have a breeze blowing against the direction of your sound is going to drift up against that air coming in. If you've got sound, or if you've got air traveling with your sound, that air is going to tip your sound propagation down. So you kind of have to compensate for that. These are just very simple concepts of how environmental conditions can affect the way that sound propagates. Yes? We're done. Thank you very much.